Hi, my name's Connor Whiting, and today I'm doing a presentation on how to predict the likeliness of malignant breast cancer using a logistic regression via homomorphic encryption on encrypted data. To start off, what exactly is homomorphic encryption? What does that mean? Well, the basic idea behind homomorphic encryption is that it provides a way to do computation over encrypted data. The benefit is obviously that it preserves privacy by securing your personal information. This is increasingly important as AI and other technology gets more powerful. Privacy is an increasing concern and security of data. An opportunity for homomorphic encryption is that it presents a disruptive technology or even a game changer in the field of AI, especially when dealing with sensitive information, such as financial or medical or etc. The challenge, however, is that homomorphic encryption is orders of magnitude slower than using plain data. The encryption itself takes a substantial amount of time, and then performing the evaluation on the encrypted data is another large chunk of time. Also, the homomorphic encryption is not 100% accurate. There is an error called noise, which results from issues in the encryption and decryption, errors or inaccuracies that cause your accuracy to go down. What's the research motivation behind my project? Machine learning and artificial intelligence are widely used in today's world, and we are increasingly seeing real-world machine learning problems which involve sensitive information that must be kept secure and out of the hands of people who would do bad things with it. This can be financial data, healthcare data, medical data, you name it. Pretty much any kind of data that is used in a machine learning problem could need to be secure. My project highlights the importance of privacy and security and investigates how to apply homomorphic encryption in machine learning. For example, model training using an encrypted data set, which is what I did specifically. So what does homomorphic encryption do? How does it work? Why is it called homomorphic? So you have a function f of x equals 5x. So this function has a property that f of x1 times x2 is equal to f of x1 plus f of x2. This is an additively homomorphic function, meaning that you can perform the function on you can calculate the sum of the function evaluated with two separate numbers and have that be equal to the function evaluated on some combination of the two numbers. The same thing can be said slightly differently for g of x equals 5 to the power of x. This one, for similar reasons, is multiplicatively homomorphic. However, an important thing to note is that neither of these are true encryption functions. In order to have a true encryption function, you need e of x1 times x2 to be equal to e of x1 times e of x2. So this is an encryption scheme that this e of x that allows you to essentially get the same result by doing two separate sets of operations. You multiply the two data points and then you encrypt them, or you encrypt them and then you multiply. The idea behind the encryption scheme is that you get the same result either way. Another key feature of the encryption scheme is that the corresponding decryption method, when you decrypt e of x1 times e of x2, you must get x1 times x2 for a multiplicatively homomorphic encryption for similar reasons. So what's the data set that I used for my project? I used a data set that contains diagnostic data for breast cancer patients. It provides measurements of relevant features in fine needle aspirate samples, along with a diagnosis of malignant or benign breast cancer. This data set consists of 569 instances, 569 separate cases with 32 features each. These features are measurements that help predict the likelihood of a malignant breast cancer. So what software did I use? I used Tensio, which is a software that enables homomorphic encryption operations to be performed on tensor. Tensors are a type of data storage that allows for logistic regression to be performed on data. It's more machine learning amenable than some other forms of data storage. My experiment was also conducted on Google Colab. So now let's look at the actual experiment. So when you do the predictive modeling training, the logistic regression, using plain data, you just take the data set, run it through logistic regression, and see what you get. you'll notice the loss at each epoch is very, very small, and the final accuracy is large. This means that that can be interpreted as 97.6% of the time, the result from the logistic regression is correct, which is pretty good. Now, when we contrast that with the similar evaluation using homomorphic encryption. So the encryption of the training set alone takes 8 seconds. You'll notice much larger accuracy drops at each epoch, and the average time per epoch is 73. With 6 of them, that comes to 438 seconds, plus the 8 for the training set encryption gets you to 446. This is a much more substantial amount of time than for the plan set evaluation. Another key feature is that the final accuracy with the homomorphic encryption is 91%. This is significantly lower than the 97.6% from the plain test evaluation, meaning that the homomorphic encryption comes at a cost. Your security comes at a cost. A runtime cost and also an accuracy cost. So the plain test evaluation of the data took 1 second and gave us 97% accuracy. So why would we want to do the homomorphic encryption scheme at all if this works? Well, the issue is it all goes back to the privacy. If you perform evaluation on a plain test and you're doing it through any sort of insecure channel, your data can be stolen. If that's sensitive medical information, financial information, credit card numbers, bank account passwords, that's really bad and can lead to serious consequences for you. So the homomorphic encryption evaluation took closer to 450 seconds, which is about 7.5 minutes. This is still a manageable amount of time, but this can quickly blow out of proportion if you have a data set containing tens of millions of data values. My data set contains about 400, which is a relatively small number compared to many real-world data sets today, which are huge. Also, the accuracy, while it's still high with the encrypted evaluation, it's noticeably lower than that of the plain test evaluation. So the question is homomorphic encryption a practical way to secure sensitive personal information? Well, if you have a small-ish data set, like something manageable that a computer can do in some reasonable amount of time, maybe like less than a day, or more if you have more time to allocate to it. That's perfectly feasible. It allows you to have the advantage of the security. You can just hit the run button and let the computer sit there and go do something else. The issue arises when you have a massive data set. If you have a data set with 1 billion data values, this homomorphic encryption is completely impractical. The runtime is colossal. Your accuracy drop will be much larger than the 6% deficit that we have for this particular data set from using homomorphic encryption. So in conclusion, homomorphic encryption it's useful, but it's really only practical on small data sets if you're doing some sort of other evaluation on it, i.e. a machine learning evaluation, logistic regression, or something else entirely. So when these days computers are constantly getting better, we're constantly developing better homomorphic encryption schemes. So this runtime, that encrypted evaluation runtime, keeps getting smaller and smaller. With a better scheme that's smaller, the accuracy will also be higher with a better scheme. And then with a better computer, that runtime will be slower, but a better computer does not really change the accuracy so much. However, the encrypted evaluation will always be slower than the corresponding evaluation on the plain test. So the key takeaway here is that privacy and security come at a cost, and you have to balance more factors than just one when you're determining how you want to keep your data secure. I would like to thank my mentor for helping me with my project and Polygence for making this opportunity possible. Thank you.